I've done that on an exam before, so no worries. Uh, I was playing a game called One More Brick, and the volume went out, and a few people knew that game, so that was wonderfully embarrassing. Make sure never to do that again. Looks like we can start. Welcome back, everyone. So I have a couple set of announcements, but I wanted to start with any questions you folks all have first. Any questions or comments to start us out today? Okay, well, let's get started. We're mostly done with this section right here. We have two more examples, or two or three more examples we want to go through carefully. Then we're going to go into trigonometric substitutions. Really, section 7.2, 7.3, there's a theme here. A really good capsule review on trigonometry in its own right. If you feel like you're struggling a bit with the trigonometry, I'll plug once again. Take a look at these notes to kind of give a feel or a refresher, or take a look at the appendix in the back of the book, are great resources. But first thing I want to point out is we now have some definite hours on the Math Center on this campus. So if you're on the Idaho Falls campus, the Math Center hours I have posted here on the Moodle website. And it looks better on the door. This is also posted on the door, room 220, that's over in that direction there. So if you're on campus Monday, Tuesday, Wednesday, then you can get help from either one of these individuals. Pageant, Randy, and myself would be very happy to take a look at those topics. For me, the way I do tutoring is I'm just in that room from 2:30 to 4:30. You can pop in at any time. Even if you popped in at 4:20, 8 p.m., I'm still going to be in that room. So I'll take a quick question before I leave for the day. There's also Murray Smith, but this one is going up to statistics. So if you're taking a statistics class, she'd be a great person to see. Yeah.
I want to mention, no, you do like an online tutoring session from hotel as well.
Absolutely, yeah.
I did one, it was great.
Oh, awesome. So if you didn't hear, the online tutoring is actually pretty good. They're just through Zoom, right? So they're using like a whiteboard or maybe a document camera to help out.
Yeah, that's what we did. Just one thing was that you need to check the person's name and see their specialties because not all of them can do calculus too.
Gotcha. So probably where you'd be going then is, let me take a look if I can find that. That's my link. You go to ISU tutoring, right?
Yeah, and you can sign up separately on the site. There's like a separate sign up.
Probably this right here. But you're saying definitely go to.
I make appointments. That's actually what I press.
Gotcha. Make an appointment, and then yeah, they'll get you set up some pretty decent tutoring. That would be really helpful for the online section. Where I mean, me saying I have office hours in room 220 is probably not helpful if you're in Pocatello or even further out. So there's great ways to get extra support. Also, don't forget, I also have here on my syllabus, you can pop in on any one of these times through Zoom if you're in the online section, and I'll be very happy to help out. Zoom office hours are for anybody. So you might see people in my other classes and so on, but it's just the same way I do the tutoring in room 220. I'm just sitting there in an open Zoom meeting until someone pops in with a question. I go for the full hour, and so if it's a quiet hour, I get kicked out at 40 minutes. If I don't notice that, you might join in an empty Zoom room, but I get an email and I just pop right in to alert me. I get an email that alerts me and I just pop right back in. Well, any questions, folks, about any of those items? Okay, that was pretty much it for my announcements. We're about to finish up section 7.2, so this due date is official. And for section 7.3, this will be an official due date if we do get it finished on Thursday. But keep in mind, all of these get revised as needed. But here's where we left off. About to take on another pretty tricky integral right here. You know, the way you study calculus is also pretty fundamental. If you're, say, beginning to do a problem set early in the morning, a lot of people say that they do math a little bit better earlier in the morning. Your mileage might vary, but it's not a bad idea to just do a quick warm-up. Let's do it ourselves right here. So this is what I mean about a quick warm-up. We're in a section where a lot of derivatives and antiderivatives are very relevant. We're dealing with trigonometry. So let's write down some stuff. You can use Newton's prime, but I want to give Leibniz notation some love as well. I'll go first. Derivative of tangent x is secant squared x. Anyone for the first two values up here? Awesome. So that's kind of what my warm up would look like to start. Let's finish out the table, d by dx of cosecant x. This one would turn into negative cosecant x, cotangent x, d by dx of secant x. Always there's a good way to think about this. If you're differentiating a cofunction, expect a negative when it's dealing with ordinary trigonometric functions. So cosecant gave a negative here, and this is the ordinary function. So go from the cofunction to the ordinary, take off the negative sign. From this, go from the cofunction to the ordinary. And from this one, go from the cofunction to the ordinary one. That's a pretty decent mnemonic for memorizing two formulas at once here. Likewise, I have a function. Here's the cofunction. If you differentiate that, definitely a negative sign. Answer would have been secant squared, but we're differentiating a cofunction, so we put in the relevant cofunction there, cosecant squared x. Kind of a silly warm-up, but I promise you, if you feel a little rusty on these, it's typical at the start of a Calc 2 class. Do that about 12 times before you start a homework set. Let me say it better. Before you start a homework set, do one of these things, and do that about 12 times on your homework sets, and this kind of stuff just becomes second nature after a while. I do, in fact, do that myself personally. If I haven't taught calculus for a little while, I just review these things, get it back in muscle memory, and then you're good to go for a while. These things are perishable, so you have to refresh them. Here's the next portion of the warm-up. Let's integrate cosine x, sine x, tangent x. Some of these you might have to look up since some of these are new, but any volunteers for the first two? Here and here? Good call. This one is sine x. I'll throw a constant here, but it's just a warm-up. So if you left that off, no big deal. I'm just in the habit of doing that, lest I forget on the other ones. So this will be negative cosine x. Good call on that one. Any volunteers for antiderivative tangent x?
Isn't it secant of x times tangent x?
Not quite. This one's actually kind of a weird one and kind of a tough one. The trouble with that is if you differentiate a secant times tangent, now you've got to use the product rule, and this starts to get even more convoluted. So this one is the weird one. There's actually an answer up there on the top of the notes, but how about anyone in Zoom? Anyone in Zoom happen to know how this one should go?
I think it's 1 over something, but I can't remember what it's over.
You're kind of close in a way. It turns out there is a 1 over something because it gets wrapped up with a secant function, which is a 1 over cosine. But this one, again, it's kind of a weird one. You can solve this by a u substitution. If you did a u substitution, you would eventually get this thing, natural logarithm of the absolute value of, oh, that would have been a mistake, secant x plus constant. I mean, that seems kind of totally arbitrary in a certain sense, but if you differentiate this and use the chain rule, absolute value falls up, and you will get a tangent x. Forgot my x in there. That could help clarify it. So again, these are good warm-ups to do because already this is something that can come up in a homework set. It can come up in an exam, but you're not meant to reverse engineer this and do the u substitution. These are formulas you can take for granted and you should take for granted. So that's not something I pick up immediately when I'm first looking at Calc 2, but something that works its way into your mind. Now, let's do some nastier ones. We derived this one in the notes. Sine x, oh, not sine, let me try again. Secant x dx. This one is the natural logarithm of the absolute value of secant x plus tangent x plus a constant. That is a tricky derivation. We did it at the very top of the notes. But it's here in the warm-up because this is our reminder. If it comes up again, and it can, on a homework set, potentially an exam set, That's the answer that we're expecting to get. You're not meant to reverse engineer this and do it from scratch. Then there's clearly a related one. Let's find antiderivative of cosecant x dx. The patterns here start to break down, but it is a cofunction, so I do expect a negative sign. And it also very, very closely matches this format. This turns into the natural logarithm cosecant x minus cotangent x plus the constant. So that's what goes on in this land, antiderivative cosecant. Last one, find the antiderivative of cotangent x dx. Anyone happen to know how this one will go? It's related to this, but it's not exactly the same. It's very close. Good call, absolutely. Natural log, sine x plus a constant. There seems to be a missing negative sign, but it's truly there. For example, if you put a power on this that was a -1, it could turn into a cosecant, matching that, and your power could come over here with a negative in front. Our author just happened to format his answers in this kind of way. But these are the things that are, I mean, this could take a few minutes at the start of a homework set. But if you do a warm-up like this, at the start of every homework set, you're going to notice that, wow, I'm saving over the course of this entire semester, like a half of hour of not looking at things in the back of the book. These are just going to seep into your mind, and all of your things you do, homework, exams, otherwise, are just going to be much more streamlined. You're not trying to focus on looking something up. You're focusing on the new concepts. But that's a kind of good warm-up that you definitely want to do at the start of a class or a start of a homework set. Any questions at all, folks, about any of those answers there? Okay, well, with our warm-up out of the way, let's get down to the problem we left off on. We want an antiderivative for tangent cubed 3x multiplied secant power 5 3x. The best advice for tangents and cotangents is just try something, but occasionally these notes are great to work with if you're dealing with the homework. So we have them here. It says, look for an even power of secant if you can find it. Our problem doesn't have that, so part A is out, no even powers of secants. Next, if your power of tangent is odd, thank goodness, then that's a substitution that will work. If the power was even right here, that's when we're doing an ad hoc method. Those are the kinds of questions that I would not put on an exam. They require way too much thinking outside of the box to fit it in a timed exam. So we're going to go with this option here. Let u be equal to secant x. Immediately right after, we want a differential. Du is going to be secant x times tangent x dx. And see, already that warm-up would be helpful since we don't have to look anything up or pause in just doing that differential there. Yeah, go ahead.
Secant x or 3x.
Oh, I made that mistake again. Thanks for spotting that, folks. I was looking right here, but that's not great advice if you have a 3x. Let's fix that right here. Bad way to start out a very first problem, but let's call this u equals, to match that feature of the problem, secant 3x. Now we're well on our way on this thing. Du, the differential, will be first the derivative of secant, which goes secant of something times tangent of something. Throw in the input 3x. For the chain rule, you have to differentiate 3x. It's a 3, I'll just put it out in front. And now you throw in a dx here. So that's our corrected differential. Thanks for spotting that issue there. Any questions at the moment to that stage? Okay, for me, I make the personal choice of, I like to eliminate that constant. So I would write this as a third, du is secant 3x times tangent 3x dx. And now we return to the original integral. And this step is a lot of writing, but it's very critical and very helpful. We're just organizing the integrand, trying to get the factors of secant and tangent lined up to make these substitutions go through. So let's look what we have. U is secant 3x. That means that's u power 5 right here. We have to give up a power of u and a power of tangent, so this should be brought down to power 4, power 2. So this will look at like this on the next step. Tangent squared 3x, secant power 4 3x. Then we have tangent 3x, secant 3x, dx. I need to remember to give a little bit more space on the right. These things get longer when you start to organize them. Now this is starting to look better. This whole thing right here, that's just 1/3 du. This is now u power 4. All we need to do is deal with that, tangent squared 3x. Notice they also provide you with a related identity that helps out. We can write a tangent squared in terms of a secant squared. But I need to recall, this is a 3x, so let's make sure to get that in the problem. Tangent squared of 3x equals secant squared of 3x minus 1. So that's what's going in this spot right here. If you like, you can skip some good steps on your notes, because this is just turning into u squared minus 1. But I'll show that extra step to make the notes more readable. First substitution in green. Secant squared 3x minus 1. Secant power 4 3x. I'm going to drop those parentheses to try to fit this in better before running out of space. Tangent 3x. Secant 3x dx. So finally, that's the whole story on this one. We just need to put in the u substitution, finalize our answer. Any questions at all to that stage? Yeah. Absolutely. I'm going to do that on the next step once I wipe out this portion right here and put in the 1/3 du. That would be okay as well. Yeah, I'm doing all mine in one line, but if you did it right here and you have a third in front, that would be okay. To start substituting piecemeal is just fine. Other questions so far? Okay, well, let's throw this in. This is now equal to. Now, going based off what you said, this whole portion right here is the 1/3 du. So I'm going to put 1/3 in front. Integral sign, there's going to be a du here. I might need to move it to make it look prettier, but that's our first substitution for that one. Now let's start off on the left. This is just a u squared minus 1. This one is u power 4. I did need to move that du. It goes right here. At this stage, if this was an exam question, say 6 points on an exam question, I'd probably give 4 points to this stage because it's mostly all said and done as far as the thrust of Calculus 2 is. We just have to go through the formality and do the Calculus 1 methods to finish this off. So let's run it through. Definitely, like we mentioned before, integrating something times something usually involves integration by parts, but if it's just two algebraic functions, just expand it and you're treating yourself to a nicer integral. This is 1/3 the antiderivative of u power 6 minus u power 4 du. Let's move that out of the way. It's also up there in the notes, so it's not deleted forever. Antiderivative here is going to be the power rule in reverse. So we have 1/3. It has to distribute through. This is a 7. U power 7 minus a 5th, u power 5. And a constant. At this stage, we could still lose a point because we have to undo the substitution, but it's a very minor last step we have to make. So here's our full answer. 1/3, 1/7 of u was this thing, so secant power 7 of 3x minus a 5th secant power 5 of 3x plus a constant. For me personally, I'd probably just leave the answer in this format. It's always your judgment call if you want to do any extra factoring, distributions, but usually that's best if you find an easy way to cancel, simplify in some way. Yeah, go ahead.
So I did a little differently. I solved for dx, where you remove the 1/3, actually solve for dx.
Dividing out the secant and the tangent.
Yeah, I can get it to 1/secant 3x, tan 3x, times 3.
Mm,
Then I multiply that through n, okay. It's the same answer, but it was already distributed, so with secant, with 7 3x and 21 minus secant 5 3x and 15.
yeah, you got the same answer there. And that is a good strategy. I think our author, for one reason or another, just usually doesn't go that route when you're reading his examples, but it's completely valid. If you divide by secant and tangent, you solve for dx, and when you put it in here, instead of factoring them off, you're just canceling them off. So your algebra looks a little bit different, but totally correct as well. Other questions about that so far? Okay, lots of different strategies. I typically pick the strategy our author uses just to make the reading more compatible. But if you learned calculus a different way, you don't have to change your methods. Absolutely, what works still works. Well, let's take a look at the last example. Sorry, question first. Yeah.
Would it matter having the seat inside or outside the parentheses?
Which part?
Like towards the very bottom, the plus C, would it matter having the plus C inside
Gotcha.
or outside the parentheses at all?
It does not matter, but it can make your work look a little interesting. Say, for example, with this plus C out here, that's how the integral would typically end up. But if we did something different and the algebra was a little bit different on this problem, and it looked like that, well, you could just leave it right where it is. If you did distribute the 1/3 in, you would have gotten a 1/3 times a constant, but this is any real number, and so is this one. People could redefine it as a new constant, call it, say, C1. Your answer would end up looking back like this in the end of the day. So whether you leave it in or out, I would say that's a stylistic choice at that point. You would still have the totally correct antiderivative, and it would still represent all families, an entire family of all correct antiderivatives. Other questions so far?
Quick question.
Okay, well, we're nearly done. Sorry, sir. Go again. I think I heard one over Zoom.
I have a quick question on the left where the green and
Oh, gotcha. Right here?
yes. How did the powers drop?
Sorry, what was that last part?
How did the powers drop down?
Oh, gotcha. The power 2 didn't really drop down entirely. With tangent squared, it just became a secant squared right here. Was your question on more about this identity itself? Just a related comment, the power of 2 through this identity got us a secant squared. So we had the secant squared there. Then with this u, the power of 2 also became a u squared.
Been talking with the tangent, the third in the beginning.
Oh, gotcha. Yeah, thanks for mentioning that. Let me go back up here. So that power of 2 was originally a power of 3, right? But once we took this differential du, we noticed that we have to give up a power of secant and a power of tangent altogether. So that's the secant right here. Or I said that weird, that's the tangent right here and the secant there. This tangent would combine with this one to give us back up to tangent cube. So that's how the power dropped down by 1. Does that make sense there, Jose?
Sort of, but I think I'll have
Gotcha. I did want to mention your audio is a little bit better. I can hear everything just fine, except like the last thing you say is somehow cutting off a bit. But the audio is definitely improving, so that's awesome. Other questions or comments at the moment?
So a good way of thinking about this, right, is if you just take the powers and then just move them into your dx essentially. So like if you take if it's tangent cubed, you're essentially just moving one of your tangents over to create that identity essentially.
I think that's a great way to say it. Absolutely. So the identity that I was trying to get to was all of that, well, maybe less the 3. Let me circle this one. I was trying to replace all of that stuff with a third du. And so like you said, we just pull a power out, power 3, move it over, so that represents du at that stage. Is that what you were mentioning there with moving the powers?
Yeah, I think so. Because like you're essentially just reorganizing your tangents and stuff because the power rule, not power rule, but you can essentially just rearrange the equation to turn
Laws
your.
it's essentially.
Okay,
Yeah,
yeah, I think that makes sense.
yeah, all this was about is just organizing what turns to du, what's left over, so we need a different identity to pull in, all to get to this stage. So yeah, this is just rearranging, splitting off powers using exponent laws, absolutely. Other questions or comments with this one? Okay. As we
Also
go through,
going, are we also going to have to remember these identities?
yes, we do need to know the identities such as, say, the fact that tangent squared at 3x turns into this one right here. So those are pretty common identities we have to memorize. When it comes to stuff like, oh, where's my scroll bar? When it comes to stuff like this up here, I'd say these identities are very non-standard, these two in particular. If these came up in an exam situation, I would provide those. So the weird stuff you don't have to always memorize perfectly. But when it comes to the more common stuff, say these types of identities, you'll notice that in the homework, this comes up over and over again. Those would be the things that we would have to remember for an exam. But keep in mind, my exams are open notes. If you feel like you need extra support with trigonometry, that could be part of the notes you include on your exam one materials. Oh, I just dropped something here. Give me a minute. The tip of my pen has come off. And if I don't find that, I might not have an easier time to proceed with the class. I've heard something over here. This is embarrassing. Well, we'll just do the best we can with a slightly damaged pen. Huh. No worries, we'll find a way to proceed. My pen seems to be broken now. I should use some glue or something on that. But other questions or comments so far? Yeah,
In the way that I did the scene makes a little more clear why the tan, when the tan is dropped off. When I'm looking at yours, it's just, it's a little confusing because see, you didn't use substitution, so you remove the secant 3x, and then you find the derivative of it,
mhm.
and then you stick it back in with U substitution. But then you remove the tan because it's in the U substitution.
This 10 right here.
Yeah, you move the U, so it becomes tan squared, so tan cubed. And you remove that because it was in the.
Well, because we had to have a, yeah, U is secant.
So, yeah, it's just interesting that, because then in mine, it ended up with tan in the denominator, and that's why I canceled out.
But after you did a cancellation, you should have still had a tangent squared, right? So in the end of the day, it still would go like this. The difference is you're doing a cancellation. I just fully substituted this out, is the differences. Does that help out thinking in those terms? Gotcha. Other questions or comments so far? While I clandestinely try to look for that pen tip. Sometimes a flashlight is what you need on this kind of thing. Here we go. Let me see if I can do a really quick scan through here. Oh dear, where did that pen tip go? Never happened before. I think I was fidgeting too much, and that's the problem. Oh, I found a Band-Aid. That's kind of gross. I'm not sure who got injured a while ago. Weird stuff you find when you start looking with a flashlight. Other questions or comments so far, folks? Okay, well, let's try one more out. This is going to be interesting, but we can still survive this. Part D says find the antiderivative of x secant squared x. This one's kind of an odd one out. Anyone see what the method ought to be to solve something like that? Absolutely. We have a algebraic function multiplying a trig function, so good call. This one's just an ordinary run-of-the-mill integration by parts. That means we need a u. Well, if there's an algebraic function, yeah, x would be a good call on that. So let's set u equals x. Well, comma there, there's a home rule, there we go. Next, du would have to be everything else. We have a secant squared x. Sorry, say again? Well, this should be a dv right here, thank you. This should be a dv here. Somehow it's easier to remember when you're writing it down versus typing, that's strange. Yes, so du will be the derivative of x, which is a 1, and then we have a dx. Here on this column, we're integrating v, and you can see what the antiderivative of secant squared should come out as. Good call, absolutely. Again, that's all about the warm-up. The warm-up, doing those derivatives really helps out with this kind of thing. So good old tangent x would go there. See if we can still color code things. I'm not going to attempt to draw too much with just the mouse. That would be kind of a bad experience. But at least we can slap things with the highlighter. That's still going to work. So this is how it starts. And everything in the integral can now be expressed as either the u or the differential dv. So if it's all going according to plan, next step I would write with this is get to the cursor tool. There we go. I would just write out the formula. This equals, anyone in Zoom know how this go? As just a formula for this stage.
Isn't it uv minus the integral of v du?
Absolutely, good call, folks. So there's our formula. Now we're just plugging in the information. So first u, that's going to be the function x. It multiplies v, so we're going from here to here. So let's go x, tan x. Let me see if I can color code some of that. So here's the u, here's the x, here's the v, and tan x. On our way, minus the integral. Next it says v du. Here's the v function. Going this way, here's the du function. It's just going to be the integral of tangent x dx. So let's plug that in. Tangent x dx. Here's the color coding for that bit right there. Now all we have to do is find antiderivative of tangent x. So here's where the problem's about to end. Just copying x tangent x to start. And minus, anyone recall antiderivative of a tangent function? Absolutely, good call on that one. Again, that was in our warm-up, also on the very top of the notes. These are just the little things that come up so often that you're eventually just going to memorize them down pat. But it's good to do that quick warm-up just to streamline everything else you're about to do. So we'll go natural log secant x. Still not totally correct. You can see what's missing. Good call. We do need our constant of integration since it was indefinite. And then that satisfies the entire problem. Hey, we did it, folks. Didn't have a pen tool, but we're going to do the best we can on this thing. Any questions at all in getting to that answer? Okay, well, that closes out the notes, section 7.2, trigonometric integrals. And you'll notice the main thing we did, part D, is the odd one out. It's all just u substitutions. So the more comfortable you get with u substitutions, the better off you are with this kind of stuff. And you don't have to do it the way I do it. This is typically what the author does. Arrange things, organize, substitute out. If you'd rather solve for the dx, perfectly valid approach as well. That works very nicely on these problems as well. Any last questions whatsoever in section 7.2, folks?
Yeah, I had one more question about the odd trigonometric functions.
Yeah.
So is it just a good rule of thumb to just have all of your trigonometric functions be even, and then everything else you pull out essentially turns into your du for your substitution?
Yeah, you want to have even here if this is the odd one out, only because these identities are now going to be in play, allowing you to remove the problem. Is that what you were mentioning there about wanting the evens?
Yeah, so because I'm noticing a lot of these are like tangent cubed, like secant to the fifth, like that last one that we did, and then we just essentially pulled out two of those functions in order to create that du. Sorry, the du. And so is that just an overall rule of thumb, or is that so I'm not asking that question very well, but do you just want even trig functions before your U substitution?
Absolutely. And again, it's mainly just because the identities involving those in even trig functions are very easy and direct. But if this was just tangent or tangent cube, we'd be kind of stuck in the water right here. So we do absolutely want evens, power 2, power 4, and so on. Other
Okay,
questions?
that makes a lot. Thank you.
Yep, absolutely. Thanks for asking about that. Anyone else with questions at the moment?
Yeah, I got a different answer.
On the one on the bottom down here?
Yeah, I got x tangent x plus natural log of the absolute value of cosine x.
Well, what's going on with that one is if you go negative natural log secant x, suddenly you're in the realm of properties of logarithms. So this is kind of exciting. You can take your negative sign right there and go natural log, absolute value, secant x to the power of -1. So a coefficient can become an exponent. This is not secant inverse. This is the reciprocal of the secant function, which would become natural log, absolute value, cosine x, once you take that reciprocal. So you're looking at an equivalent algebraic form, essentially, for that one function there. The bad news is, our author even makes a mention of it. You will find that happens a lot on these homework sets. There's very, very often many different algebraic forms, sometimes because there's more than one U substitution that works. So there's two great answers that you can have. So that just becomes a really common experience. But if it's a logarithm, that's probably what's going on in that case. Any other questions so far, folks? Okay, let's close this notes. And we're still reviewing trigonometry when we go into section 7.3, but we're getting over the hump at this point. So let's take a look at how that goes. This one's called trigonometric substitution, but what's cool about that is it's just U substitution, slightly different than you may have seen in the past, but in essence, that's all that's going on here. This is kind of a shorter, more direct section. Section 7.4 on partial fraction decomposition is a little bit longer. I mean, it just sounds longer to say. But this is something that could have been kind of like an add-on to section 7.2. So there are certain expressions that come up whenever you're integrating that just cause all manners of problems. Sometimes if your square root involves this, or this, and it's conveyed with other things in the integrand, an ordinary U substitution can be tough or just requires so much ingenuity, it's just no longer worth it. But these kinds of things, when they do come up, they might remind you of certain trigonometric identities. 1 minus x squared feels an awful lot like 1 minus sine squared, for example, as long as you make the right substitution. So if you put in a sine theta, then using this identity, cosine squared could emerge right here. And if a cosine squared emerges with the right domain on the angle theta, you can get this entire square root taken out of the problem. That's the whole gist of trigonometric substitution. Our goal today is to practice out a few of them. We'll go slowly and carefully, see how they go, and we'll come back tomorrow finishing off this section. Any questions at the moment before we give it a try? Okay, well, here's the table. And when you read these off for the very first time, usually you're trying to look at what format does your problem look like for the square root expression. We have a constant minus a variable to the power 2, meaning we're thinking about this substitution. In place of a squared, we just have a 1. Sure, that's a 1 squared. But that means our substitution is just going to be x equals sine theta. So we'll start off by doing that. Let's see, I want to try to, because I have broken my pen tool, let me go like this. This might be an easier way to organize this information. So on the left, we're solving the integral. On the right, we're doing whatever related computation we have to do. Starting off, we'll substitute x equals sine theta. This is a weird substitution. It's still considered a U substitution, but there is no U here, and our author likes to think of this as an inverse substitution in a certain sense. But just like the u substitution method, once you have x, you need right away its differential dx. So next line, differentiate or find the differential, we'll have dx here equals, take the derivative of sine, we'll get cosine theta. Because the variable here is theta, to finish out the total differential, we need to put in d theta. So far so good. Oh, by the way, the revision was I forgot the dx there. That should always be there for the integral. So now we know what x is going to be. That's just a sine cubed. Dx is going to be cosine theta d theta. So that's interesting. We just need to say what happens to that. Let's see if I can color code that thing. How about yellow? Well, this one's a bit of algebra, but we can say square root 1 minus x squared is going to turn into square root of 1 minus, go back to the x substitution. X squared is just now sine squared theta. But if that's a sine squared theta, note the identity is back on the table. Square root of, square root of 1 minus sine squared theta just becomes square root of cosine squared theta. Sorry, say again? Absolutely. But this one is actually a bit tricky because if you're thinking of properties of algebra, we have an unfortunate formula in the background that I feel like it never gets enough attention in algebra class. The formula is that the square root of a squared is in fact the absolute value of a. I don't know how a changed, there we go. So we have to justify how do we drop the absolute value? Well, first we have to put it in, absolute value, cosine theta. And now let's take a look at the domain. The domain is kind of interesting here. First, notice that we are integrating only a real valued function, so x cannot be larger than a 1 for sure. If it was, it's out of domain. That would be 1 minus, say, if that was a 2 up there, 1 minus 2 for a complex number. So 1 is as high as you could ever go. And on the domain here for theta, in our substitution, pi over 2 is the maximum you take. But note, sine at pi over 2 is a 1, matching that upper limit. So this domain is actually really kind of important. And if you were to look at the graph of a trig function, let's do a really quick graph. Let's take a look at our cosine function right here. The theta there will inherit the domain from this first row of the substitution. So we want y equals cosine, let's just call that x. We're going from negative pi over 2 less than or equals to x less than or equals to pi over 2. And on that domain, well, cosine is always positive. That means absolute values fall off and we're in business. It really is just cosine theta. So while the domains, you might notice we don't use them directly as often when you're solving these problems in a homework setting or an exam setting. But the purpose of them is to ensure your algebra is actually working as intended, that you really get the cosine theta in this kind of problem. So let's take a look at what we've got. That's the worst part of the problem, dealing with the square root, but that square root has turned into cosine theta. We can maneuver through that. We can figure out x cubed, and we have a formula for dx. Let's see if I can highlight that one. Our dx formula is just going to be cosine theta d theta. So we're ready to start integrating this thing. Any questions at all, folks, with the organization on the right? Okay, so here's step 1. This is going to be equal to, and I don't think we want red, let's fix that. There we go. This is going to be equal to the integral from, well, we actually have a problem right now. I want to say 0 to 1, but that's relative to the variable x, and we're going to get a new variable theta. That's one extra correction we should put right in here before we get too far ahead. So before we put in everything, we're now changing the limits of integration. My lower limit is a 0. Let me put here a note. changing limits of integration. So starting at the lower limit, actually, let's go to the upper limit. I think that's usually the order I go. When x equals 1, what happens there? Well, that will imply, I forgot how to get my right arrow. Just going to go like that. There we go. That does the job. If x equals 1, that implies you're throwing a 1 right exactly there. 1 equals sine theta. Now we think back in trigonometry, what angle theta right here within this domain produces a 1 for sine? Well, that would be right at pi over 2, right? Right at the top of the rotation, sine takes its maximum value of 1. So this implies theta equals pi over 2. That's our new upper limit of integration. 1 transfers to pi over 2. Then we just redo the whole thing again. Lower limit is 0 for x. That then implies, well, where does 0 go? Always go to the very top, your original substitution. Right there for x. 0 equals sine theta. What value of theta would produce a 0 here? Any volunteers for that angle theta? Absolutely, sine of 0 is 0. So like you said, that implies theta equals 0. Okay, so we have lots of stuff here so far. Sorry, go ahead.
Doesn't that also equal 0?
It does, yeah. 180 would be pi radians. And the only reason we didn't use that is we're constrained only up to pi over 2 right at the top. But good call, there are typically many solutions to a trig equation like these here. Other questions or comments so far? Okay, so we're back on track. We have a terrible integral to look at, but with the right substitution, with the guidance up above here, here's how it starts to come together. We're integrating from a lower limit of 0 to an upper limit of pi over 2. So integrate 0 to pi over 2. Next, x cubed. Just go over here, cube your x. That means it's a sine cube theta now. Next, go to where it's highlighted in yellow. That one just turns into a cosine theta. Let's put that one in yellow since that's kind of the major thrust of what we call trigonometric substitution. Finally, we've got more. With trigonometric substitution and U substitutions, I like to organize, sometimes just by putting a multiplication sign to convey the dx is now turning into this, cosine theta, d theta, and that's our full substitution. Let me put that in blue, just to show that one here. It's kind of tricky here to do by hand. Let me see if we can just slap it with that. There it is. So that's kind of step one. Change the limits to your dx and then convey it in the integral. Yeah.
Where did you get 2 cosine thetas?
Well, the first cosine theta came from the yellow highlighting, that square root equation right here. But then we also had to remove our dx. So we threw in the cosine theta d theta from there.
Yeah.
Other questions or comments so far? Weird substitutions, right? These are a lot of the weirder kinds of U substitutions we've seen so far, but they can become familiar over time. Yeah, go ahead.
So you put a multiplication sign, but it basically is sine squared theta times cosine squared theta.
Yeah, that's what we're going to put in on the next step. Yeah, now we're just simplifying, and notice what we've done. Horrible integral, you never would really see in a Calculus 1 class. Now it's a section 7.2 integral. We're just regressing backwards as we go. We could have done this at the start of the section 7.2 notes. It would have been a routine problem. So let's finish this off. Equals integral from 0 to pi over 2. Now it's sine cubed theta, cosine squared theta, as you said, d theta. But that means, well, we're beyond the trigonometric substitution. We're solving the trigonometric integral. which means we need a whole new approach for that. Let's put a little break here. Oh, that does not work on here. So I'll just go with that strategy. Okay, now we're using a new method. Now, when it comes to u substitutions for trigonometric integrals, if it's sines and cosines, you're looking for something odd if you find it. Once you found it, your u substitution should be the opposite function. I claim a good substitution here is u equals cosine theta. If that's our u, let's check out the differential. Du is negative sine theta. D theta. And if you like, depending on the steps you take, some people mention class, they're solving for d theta, so divide by negative sine. The author would typically factor out a power right here, and then just work with this, solve for sine theta d theta. Let's leave it up to the class. How would you like to see it done? Kind of the author's way, or divided out sine theta? Either approach is equally valid. Any preferences one way or another? We'll go with the author's way. Sorry, say again? I would just use an ordinary cosine theta. But you know, cosine squared could work on that. We just have to check out the differential, see what happens. You would get a 2 cosine theta negative sine theta altogether. And that could be a potentially good one to work out. But okay, let's leave this as du negative du equals sine theta d theta. Now we come back over here, and this is the step where I'm just organizing, but this is a definite integral, so you save a lot of time just by changing limits of integration again. Essentially, if you can get away with it in a definite integral, you do not want to go back to the original variable. We'll see why in the other examples, it's not actually straightforward for trigonometric substitution. Best to keep it as variable u. So let's change our limits of integration again. Upper limit is theta equals pi over 2. So what then happens? We're putting pi over 2 right in here for cosine. That means u is going to be equal to cosine pi over 2. Cosine at pi over 2, any volunteers for that answer? Absolutely, this one comes out as a 0 altogether. So our upper limit is now 0. That was so fun, we do it all over again. Lower limit, theta equals 0. That will imply u equals, go back to our u, plug 0 in here for cosine. Cosine 0, in this case, we get 1. So we're now integrating from 0 to 1 in that order. That might feel a little bit odd, but that's how the math falls out. So back to this integral. I don't know how this is turning red. Let me fix that again. Digital ink is always a little bit easier as long as the technology doesn't break. So this is equal to integral, negative sign in front, integrate from 0 to 1 in that kind of way. I have the negative sign right here, since we are replacing all of this right here, sine theta d theta. Yeah, go ahead. Absolutely. That's going to be the next step that you could take, which I agree is probably a pretty good idea on this one. But you know, I think I did skip a step I usually would want to take. We could put it all together right here, but let's actually organize the integral a little bit. So let me back off just a touch. Still integrate from 0 to pi over 2. Let's take another look at what we've got. If u is cosine theta, then we have no trouble right here. That's just now a glorified u squared right in this position. So we're good right here. But now, when we go to take the differential, we have to pull away an extra factor of sine theta. So this sine power 2, right by the red dot, let's call this sine squared theta. Next, cosine squared theta. I'm putting a multiplication symbol right here just to organize. Where it was sine cubed, I'm throwing in sine theta, d theta, because now the sine theta d theta reminds me of this part right here. We're going to replace it all with negative du. So that's a good step to always put in the middle. Bad one to try to power through, I'd say. But notice what also is a problematic thing here. Right there, we have sine squared, and he was meant to be a cosine. So we need even more issue or more information in here to correct that issue. Let's put it right here. And oh, what happened to my pi? This equation stuff can get kind of annoying after a little while, but we're just about there. So over here, let's deal with this thing. The only thing that's odd, the odd one out. We have sine squared theta what would you all say is the identity in this situation that we ought to use? Absolutely. This will turn into 1 minus cosine squared theta. So let me see if I can organize this even a little bit better. So in yellow, we're going to put in that substitution right here. It's going to turn into a negative du. In green, we definitely know what to do with that. That's going to be a u squared. The only thing left over that's a little bit vague still is running out of colors, but purple should work. Sine squared theta. That's incompatible with u until you put in that information right there. So this is what's going to allow everything to go through and give us an answer finally. So let's write this in. So now it is equal to, first I'm going to deal with the thing in yellow. That means I'm putting in a negative. I'll throw this way out in front of the integral. Integrate from the lower limit is now 1 up to the upper limit, which is now 0. So now we replace our thetas. In here for sine squared, we have 1 minus cosine squared. This will turn into 1 minus u squared in that position. Does that make sense to folks in that substitution? Okay, jumping through a lot of hoops, but you know, that's a lot of mathematics. Substitute this and that. Yeah, go ahead. Oh, that's a nasty thing to have on there. Thanks for mentioning that. Let me see if I can correct that. Aside from purple, what do we have that works here? How about that? Let's go with that one. Thanks for mentioning that. It looks good to my eyes, but I'm not looking at that, which has different color corrections going on here. So that's good information for me. So we did that sine squared, which means it substituted in right to that position. Cosine squared, that's just now a u squared. And in yellow, only thing I have to last put in is the negative du. Negative is already in front, so it just goes like that. Let's see if we can fill in the rest of that color. So here and here is all the moving parts. The only thing I didn't have a color code for, just ran out of colors after a while, is the limits of integration. So if we can solve that, we're on home free. So this was 7.3, trigonometric substitution. Turns into the last section we just finished, trigonometric integral. And then we wind it all the way down to a calculus 1 problem. And we will not undo any substitutions. From here to here is a great way to integrate. But I like the comment made earlier in class as well. Those limits look funny, right? They look out of order, but it's totally valid in calculus. If you don't like them, you can change the limit of integration. You just have to multiply by -1. So if you force this positive, it means you're integrating from 0 to 1, the same function as above. Let's go that route. It's not required at all, but sometimes if you can kill a negative sign, it does simplify things down. Next, we want to distribute your u squared through. So we have u squared minus u power 4 du. And let's just get the total answer at this stage. Antiderivative of u squared is a third u cubed minus antiderivative of u power 4 is 1/5 u power 5. This entire thing, there's a trick for showing this, has got to be evaluated. I don't want to try to draw that though. Where is my equation editor? We want a bracket. This is the most tedious way to do math ever, but if you're ever in a position where you have to write a math exam, if you're ever teaching math, not bad stuff to pick up. There it is. That'll be my bracket. We're going from 0 to 1. And that's the thing we're going to resolve. So let's write this out, last step. Equals. Upper limit is 1, so this will turn into a third, minus a fifth, minus, with parentheses, the lower limit is 0. So I'm just writing that out just to show what the structure would be, but it's just 0 minus 0 at that point when we substitute it in. So we have a third minus a fifth. And this in total is going to turn into, let's see, 2/15 at the end of the day. So the area under this curve from 0 to 1, my claim is it's exactly 2/15. Kind of weird, but we've got it, folks. Any questions about this wild process so far? Okay, it's a little bit weird. It comes together in a lot better way the more you practice it. But the idea is we're trying to eliminate a square root just to make integration straightforward. And integration's weird. Sometimes it takes a lot of trickery to fix one tiny problem in your integral. I want to mention, these are the ones you definitely want to be dealing with if you're dealing with a homework problem, because there is an extra complication on this one. This one is indefinite, which means after we do our substitutions, we must unwind them and return back to the original variable x. Turns out that's not completely easy. It is a new technique we have to consider, but it's a good review of right triangle trigonometry now at that point. So if you're thinking SOHCAHTOA, you're already a step ahead. We have to use that on the next problems. Well, I broke my pen. I'm going to try to find my pen tip. This is kind of a painful way to do math, so I think we'll call it right here. Does that sound all right to folks? Okay, I think these problems take like an extra 10 minutes without the proper tools to write these things down. But I'll see you all on Thursday. We'll just be on part B on these notes. Probably rolled somewhere clear over there. Who knows?
Thank you.
Thanks. You can just drop it wherever you like.
Do you have some questions?
Oh, sure.
So we got an option here. So on this one, problem 11, I was working through this and the answer depended on this. It shows another -2 sine x.
Oh, I see.
I didn't understand where that came from.
Oh, let me see the work here. Maybe you can see how that could have came together. So it looks like you're doing the integration by parts. You're missing that pen tip. That seems weird. That's a good choice for you. Du would be 2x plus 2, so that looks good. So this would be cosine x.
Cosine x.
Antiderivative should be, well, on this one, it should just be a positive sine x.
Okay.
Because the derivative of positive sine would give you that cosine. So it looks like it might be up to that negative sign right there.
Okay.
That makes sense with that one?
That does make sense.
Cool. Work looks pretty good on that though, other than, negative signs always causing havocs.
That one's due today, isn't it?
Oh, actually, that one is due tomorrow, I believe. Yeah.
Fix it then.
You do, yeah. And I'm not really being firm on the due dates. They're really just a pacing guide. So if this was Thursday, you need to make some corrections, that's okay to take extra time.
Sweet. Thank you very much.
Yep, you betcha.